Our next smart contract allows users to offer an amount of one token to exchange for a desired amount of another token. For example, Alice wants 100 dog tokens and is offering to swap 10 USDC. Without our program, the users would have to swap with each other manually. But what if Bob promised to send Alice 100 dog tokens but took the 10 USDC and ran? Or what if Alice was dishonest, received the 10 USDC and decided not to send the 100 dog tokens? In the traditional finance world, when Alice swapped with Bob, there would usually be someone in the middle holding the funds temporarily and taking a percentage of the transfer for themselves. But in blockchain, this is solved with a swap program, also called an escrow. Our program will transfer the funds provided by Alice into a vault account and store details of her offer, like the amount and type of token she wants, in another PDA. When Bob decides to take the offer, our program will transfer Bob's tokens to Alice and transfer the funds in the vault to Bob. Now remember, in traditional finance, someone would sit in the middle, taking a couple of percentage points of what Alice and Bob are offering. But with our smart contract, Alice got 100% of the tokens Bob sent. Bob got 100% of the tokens Alice sent, and they got what they wanted without having to trust each other. Fees were only a fraction of a cent. That's the benefit of decentralized finance. Let's get started. So let's make a swap program. First thing I'm going to do is run anchor init, swap, and I'm going to use the multiple files template. Because this project is a little bit larger than, say, our favorites program, multiple files will split our program up across different files and directories just to organize our project a little bit better. So -- template equals multiple. Give it a moment to install. Great. I change into that directory. And let's open up our editor and have a look around our new project. So here's our project. The actual anchor program is in the programs swap directory, and the TypeScript tests are in the test directory. Programs swap is also a little bit more interesting than the normal single file layout. There's still a librs, but helpers that are specific to each instruction handler live in the instructions directory. There's a state directory for storing basically the structs for the accounts you're going to make. A constants file, I should say. And yeah, it's just this will make things a little bit neater for us. So the first thing I'm going to do is add some dependencies, because we're not just using Anchor here, we're also using Anchor SPL, which helps us do things like transfer tokens around. So let's do that. Let's pop open cargo.toml, and just where it has the anchor lang, we're going to change that to look kind of like a little object. We'll say version equals 0.30.1, and we'll also turn on the features equals init if needed. Init if needed allows us to create an account, add an address if it doesn't already exist. We'll also add our Anchor SPL. And what version? The same as our version of Anchor. So 0.30.1. And we may as well just say the current version of Solana program as well. It was 2.0.3. Great. So we now have our program with Anchor and Anchor SPL installed and the init if needed feature turned on. I'll just fix that typo. Great. Something else is we should probably also look at setting up our constants. I'm a big fan of avoiding magic numbers when I program. So if someone else is reading my code, I don't want them to see 8 plus 32 plus 32. I just want them to see variables that make sense to them. So in Anchor, I'm often adding 8 to things to get the true size of an account on chain. That 8 bytes is the anchor discriminator. So I'm just going to do pub const anchor underscore discriminator, and that will be a, what is it? A U size. So just whatever the size is for the platform. And it's 8 bytes. It just saves us having to reference that anywhere else as well. Oh, and I'm missing an equals sign there. There we go. Great. We're also going to be transferring some tokens in this project. So let's create a helper function that just does that for us. That way we don't have to cut and paste everywhere. Instructions, new file, and we'll call it shared.rs. And in this file, we will create our transfer tokens function. So that's just going to be pub function transfer tokens. And we're going to take this generic, which is the Rust lifetime specifier. This is telling Rust how to hold onto a bunch of the variables inside this function. And what we're saying with this lifetime of info here is just hold on to them for as long as you need to hold on to the underlying Solana account info object. If you don't know what that means, that's fine. This is not a Rust, and it's not a Rust course. This is a Solana course, but you can read up about Rust lifetimes in the Rust book. Cool. So we're going to say from, and that's going to be a token account. Token account is fine if we wanted to make our project specific to either the old token program or the new token extensions program. But if I wanted to make my program work on both of those, then there's a thing called interface account, which is just a way to have our program work across tokens that are made with the older token program or the new token program. That will last for as long as info does. And you can see here how we wrap around our token account. We're also going to borrow that value as well. We should add a return type for this function. So it's just going to return a result of nothing. That looks nice. We should probably also, for our share.rs, we should actually expose it from our module because I can see that everything is a little bit dark and gray here. Let's do that too. So we've got pub mod initialize and pub use initialize. Let's change that to pub mod shared and pub use shared star to expose everything inside shared.rs. And you can see that the gray has gone away now. You can also see that interface account is red if, Anchorlang prelude interface account. That looks good. Yeah, I think we want that. In fact, we can just import all of the anchor prelude because it's kind of a bit of a normal anchor thing just to import the entire prelude. That gives us all the what people often call the goodies from Anchor without having to type the full path to any of them. We'll probably also need to import a bunch of things from Anchor SPL. So let me do that, like token account. And we want to import it from Anchor SPL token interface because that is the magic that allows our program to work on both the older token program and the newer token extension program. That is looking a little bit better. I'll just fix a little typo there. And I will also turn on word wrapping so you can see what I am doing. There we go. Cool. So there's still a little bit of red there, but it's just saying that we're not returning a result yet, which is true. We're not returning a result. I'll also neaten this up a little bit. There we go. And let's add more of these options for our transfer tokens function. So we have a from, which is an interface account. We'll also have a to, which is an interface account, also wrapping around token account. An amount, which we will also borrow, and that will just be a U64. A mint, which will be a pub key. Same thing, we'll do interface account. Oops. And we will, it's going to live for the lifetime of the account info object, and it will be a mint is the anchor type we're using there. We'll have an authority, which will be signing this transaction. So borrow signer, and that has a lifetime of info. We'll also have the token program be one of our options as well. And the way we say that, to say that our token program can be the older token program or the newer token extensions is interface. And that lasts for info. And then we say token interface. There we go. That looks good. So the way we actually transfer tokens is we call the token program's transfer checked function. Transfer checked just does a little bit of logic, making sure the mints are okay, and a bunch of other useful safety features. This is the reason we use Anchor, because it provides us with this good stuff right out of the box. So the first thing we're going to need to do is specify all the options we want for transfer checked. We'll just get them from the options we had for our argument. So we'll say transfer accounts options, and that's a type called transfer checked, a struct called transfer checked. So in Rust, sometimes you have structs, which would be interfaces if you're familiar with, say, TypeScript, that have names that kind of seem like functions. All that means is that that struct is an object that is used as an argument for that function. So we're about to call a function called transfer checked. The options for that function are called transfer checked in title case. Just a bit of a kind of cultural thing in Rust. I would probably call this, if I was writing this in TypeScript, I would call this something like transfer checked options. But in Rust, it's just transfer checked in title case. That's the options for the transfer checked function. Because we're calling just a program in raw Solana, we're not doing any anchor magic here. We're going to turn everything into the low-level Solana account info object. So you'll see it's transfer checked. From will be the same as from, and just to account info. And mint will also be mint to account info. You might be surprised to find out that to is to account info. And our authority is also the authority dot to account info. We do this once because we don't want to have to run dot to account info a bunch of times throughout our program. So that is our options. So we should just call it transfer. Yeah, that looks good. We can call it transfer accounts options. That's fine. So our CPI context. A CPI context is just a really the program you're using plus the options. That's a CPI context new, and we have our token program. And guess what? It's to account info and our transfer accounts options. And that looks good. We've got a little bit of red here. I think it just wants us to import mint, and we want to import mint from the token interface option. It's that one there. Likewise, transfer checked. We want to import that also from the token interface as well. So, SPL, token 22. Just see if that looks right, because it that should just be transfer checked. There we go. We don't need any special magic there. Anchor SPL, token interface, mint, token account, token interface, transfer checked. So there are similar imports in other places. We want to make sure we're always importing the ones from token interface. So we have our CPI context, which is our program that we're about to call plus all the arguments. Let's actually call our program. So we do transfer checked. And the CPI context, the amount, and the decimals, which we'll get from the mint. And that looks pretty good. We just need to import transfer checked. And again, we want to import it from probably from token interface, I think. So we'll just do it manually. transfer underscore checked. And that looks good. No red. Everything is importing from either Anchor Lang itself, just for the prelude, and everything else is imported from Anchor SPL token interface. Great. So we now have this reusable function wherever we need to transfer tokens, and we're going to call it a whole bunch. So that is useful. Let's also think about what we're going to write to the blockchain. As we talked about before, there's really two parts to this. There's a make offer instruction handler, which will send tokens into a vault and write information about what the person wants in exchange for those tokens. And there's a take offer instruction handler, which will allow somebody to take the tokens from the vault and also send their tokens directly to the person that made the offer. So in state.rs, we're going to make a little file that talks about what that offer should look like. And we're going to call it offer.rs. And we're going to import our Anchor prelude again. Oops. Use Anchor Lang, ding ding, prelude, ding ding, star, ding ding is just a personal thing I use to refer to the double colons. And then we're going to talk about what that actual offer looks like. So that's going to be a struct, pub struct offer. This is going to be an Anchor account, obviously. So we add our hash account macro. Also, we want to easily be able to work out the size of what an offer is, because we're going to have to write one of these out to the chain at some point. So there's actually a useful thing in Anchor that's called init space, which is the size taken to initialize or create this account on chain. So if you add derive init space, our offer struct, or any instances of our offer struct, now have an init space property that is added to them, or an init space trait that is added to them in Rust terminology. As we said before, this is the offer where we save details about, who's making the offer and the tokens they want, etc. So it's going to have an ID, which we'll just use a numeric ID. U64 is fine. A maker, which is who made the offer, and that will just be a pub key. The mints of what they are providing and what they want. So we'll call that token mint A, and that is a pub key, and I will copy that line down, shift option down. Token mint B is also a pub key. We have token B wanted amount, which is how much they want in exchange for what they've put into the vault, which is a U64. And also, because this is a PA, we want a bump, which would just be 8 bytes. Add that missing pub, and everything is gray because I haven't actually exported the contents of offer.rs. So back in state mod.rs, I will add pub mod offer, and I will say pub use offer, everything inside. And you can see now that offer.rs looks a little bit better. What is that? Oh, I've got a semicolon on the end there. I don't need that. There we go. Nice. All the red has gone away. We are ready to move on. So we've just made our offer, which is what we're going to write to the chain. And we should probably get started on our instruction handlers. So let's open up librs and just have a look at how it looks. It is essentially the same as most other Anchor programs. There's a bunch of imports. We say our program's ID or program address. And then we have this module that we turn into an Anchor program with the program macro that defines all our instruction handlers. There's one instruction handler called initialize. Let's turn that into our make offer instruction. So I'm going to call it make underscore offer. I'm going to change the spelling of CTX to just be context. That way I don't have to think about it being spelt slightly different. And it's going to be a context of make offer. We'll call our accounts for make offer rather than calling them initialize. Again, I don't particularly like calling structs things that like verbs like make offer, but it's a bit of a Rust convention to if a program or a function has some options, then those options are named after the function just in title case. So inside our make offer instruction handler, I'm going to call two helper functions. The first will be instructions make offer, and we'll call that first function send offered tokens to vault. And we add a little question mark on the end to say, if this fails, throw an error, and that's okay. We expect that maybe it will fail in some cases. And our second function will be called instructions make offer save offer. Examples of failures in sending the offered tokens to the vault was, say we tried to someone was trying to reinitialize an old vault account. We would throw an error in that function. So that question mark is just a way of saying, hey, if it throws an error, that can happen. We expect that. It's a short way of doing error handling. So we have send offered tokens to vault and save offer. That looks good. We should probably make offer. That sounds good. I think it's it's looking for make offer and it's not finding it, so it's not happy with that. So we need to make the make offer struct, which is all the accounts that will need people to specify that they're going to use when they want to use the make offer instruction handler. And we also need to make the actual make offer file. So in instructions, let's rename our initialize. And let's just call it make underscore offer. There we go. And happy to do any edits for us. VS Code is just updating mod.rs to specify that file is now called make offer rather than being called initialize. Back in makeoffer.rs, what used to be called initialize.rs, we're going to rename that to make offer. That struct up the top. And we will also rename handler. We'll turn that into our send offered tokens to vault instruction. And we'll work on that in a moment. Let's just start with make offer. What kind of accounts will people need when they're calling this? Firstly, we'll need their own account because they're going to sign the transaction. So we'll call that the maker. That's pub maker. And that is a signer. Similar to before, we're going to use this info generic, which is the Rust lifetime of an account info object, to tell Rust that the lifetime of these variables in memory will be the same as the underlying account info object. So we have a signer of info. And because this the maker will pay for the transaction, their account needs to be mutable. So let's do account mute for mutable. We will need to have the mint of the token that they're putting into the vault. So we'll call that pub token mint A. We're going to use an interface account again, just to say this could be an old a mint account from token program or a mint account from token extensions. So interface account, and the lifetime is the lifetime of the underlying account info object, and mint is the object we're going to effectively wrap around. We'll also make sure that the token program used to mint that is what we expect. So we'll say mint ding ding token program equals token underscore program. We've done our import, and now we're going to have the other mint, which is token mint B. I'm just going to copy and paste that one, and it's going to have that same check that mint token program equals token program. So that's the type of token that we want, token mint B. We'll also specify where the tokens that we are about to put in the vault come from, which is maker underscore token underscore account A. That will be an interface account again, so wrapping around token account and lasting for the lifetime of an account info object, the underlying Rust account info from the Solana crate, rather than Anchor has nice names like token account, mint account, etc. Whereas the Solana program crate just calls everything an account info object. We're going to add a few anchor checks to maker token account A. The first is that it's going to be mutable because we're going to move files out. Well, not files. We're going to move tokens out of that token account into the vault. We'll have a few checks as well. Associated token mint must be token mint A, and the associated token authority, fix that typo, equals the maker. In other words, this account actually needs to belong to maker, the person signing the program. And associated token program should be equal to token program. That looks good. I'm going to keep going because I've got a little bit of red there, but I need to finish some more things off before I look at it. Pub offer. So this is the offer account which we will be making. That's just an account. So we call it a system account, so nothing particularly special. But we will add some anchor checks, because this is this PDA where we're going to save details about what we want in exchange for our tokens. So we'll say init, i.e. make it, who will pay to create it, which is the maker, i.e. the person who signed this transaction, how much space we're going to allocate, which is 8 bytes, anchor discriminator, that's what we made in our constants rs before, plus the size of offer init space. So the size for everything to store an offer struct. Seeds will be the bytes of the word offer, the key of maker, the pub key of maker, and as a reference, the ID of the offer, and we need that to be bytes, so let's turn it into little endian bytes, and then also as ref. That looks good. Oh, and finally, because this is a PDA and we want to be efficient, we will save the bump. That looks good. Got a few things we probably need to import. Let's go and check. So we've got our anchor lang prelude star, and we're importing a few things. Oh, wait a sec. We're importing a few things from our anchor SPL token interface, but we probably should be importing a few more. I would say actually we want from anchor SPL, firstly, yes, we're happy with token interface mint, but we probably also want to import associated token. Thank you very much. And rather than just mint, we'll also want token account and token interface. That should be good. Let's add a semicolon there. And then there we go. A couple of those we're not using yet, but that's okay. So we've added those imports, and you can see there's a lot less red there. And again, always using token interface rather than some of the other imports, just so we can have that compatibility with both the older token program and the newer token extensions program. So we have our offer. We need to also use the vault account because when we make an offer, we're gonna say details of the offer, and we're gonna put our tokens in a vault account. So let's do pub vault. And that's also going to be an interface account with a lifetime of info. And that will be a token account because it's just going to store some tokens for us. Let's add some anchor goodies as well, some little checks on that account. Firstly, we're going to need to create it. So init. We don't say init if needed because we don't want anyone to be able to reuse old vaults. We'll say who is going to create the account, which is the maker. And we're going to mention a few checks that we're going to do with this. And I'll copy it from maker token account A. We're going to make sure that this token account's mint is token mint A. The authority will not be the maker. It will actually be the offer. So this token account isn't owned by a user. It's being owned by our program. Specifically, actually, its authority, rather than its program owner, is the actual offer account. So the vault account is owned by the offer account. The vault's authority will not be maker. The vault's authority will actually be the offer, because the offer PDA is going to each individual vault will be its authority will be the offer account. The offer account will sign for things to move things in and out of the vault. So you'll see that later on when we start transferring tokens around. And we'll also check the token program is the token program we expect. Finally, we're just going to specify the accounts of the programs we use. So like the system program, system_program. There's a program account. We'll use it for the lifetime of info and system. And likewise, we'll also use the token program. That will be another interface account because we're going to wrap around to either the older or the newer, older token program or the newer token extensions program. So that's token program is a interface. Sorry, it's not an interface account, it's just an interface over info and token interface. We can actually make our project a little bit smaller by excluding this stuff, but it is best practice, so that's why we've included it in this tutorial. Finally, we have the associated token program, which is the program that maps associated token accounts to their owners and to token mints. So associated token program is a program for the lifetime of info and associated token. There we go. So that looks pretty good. It's saying it doesn't like ID, so let's go fix that. We need to actually say in this struct that we want access to the ID that the client provided when they were making their instruction. So we will scroll up and we will say we want access to, what was it, instruction. We want the ID parameter, which is a U64. Save that. And you can see the ID green has, the ID red has gone away. Anchor discriminator, it looks like we didn't import that. So import create anchor discriminator. Thank you very much. Sorry, offer is not an account of system, is an account of offer. In other words, offer is the struct and in our we are specifying that the offer account is an instance of that offer struct. So yeah, our whole make offer is complete. There's no red. We now need to work on send offered tokens to Vault. So let's make send offered tokens to Vault. This is actually a pretty small function. It's going to take a context, which I will spell properly. And so it's going to take a context of make offer, which we will actually borrow because we don't need to write to it. And what else is it going to take? Probably the amount of tokens. So token A offered amount, which is a U64, right? There we go. And we're going to get rid of the logging there. We're just going to say transfer underscore tokens. Oops, tokens. And we will say our options for transfer tokens. So the first thing is context. I think I might need to import this actually. Is it complaining that I need to import this? No, it's just saying that we, because this is going to return a result of nothing. We can't. There either needs to be a semicolon there, and we go OK, or we can just remove the OK because transfer tokens returns nothing anyway. So there we go, and it's saying that transfer tokens is not imported, so we need to import it. And it looks a little bit happier now. It's just saying that we need to give it the right arguments, which is what we're going to do. So we're going to borrow context dot accounts. This is going to be our from. It's going to come from maker token account A. And it's going to the vault. So context dot accounts dot vault. How many tokens? Well, that is the token A offered amount. What's next? The mint. Mint will be the context dot accounts, and that will be token mint A. Authority will be the maker, so that's context dot accounts dot maker. And the token program will be whatever the person running the instruction has specified. So context dot accounts dot token underscore program. Save it, and we've filled in all our details that our transfer tokens functions wants. There is no red in the file. We have now created our send offered tokens to Vault instruction, and everything in that file looks good. Let's add the final part of make offer, which is that second function called save offer. So pub function save underscore offer, and we'll use the context again. So it's going to be a context of make offer because we want access to all those accounts. So we have our context of make offer. We're going to have an ID, which is that U64. We're going to need to specify how many tokens we want in exchange, which is token B wanted amount. And that will also be a U64, and they are all our options. So this will return a result of nothing. And here is our functions body. I'm just going to turn on word wrap so you can see a little bit easy. There we go. There's a little bit of red there. It's just saying that we haven't returned a result yet, which is true. So we're going to call context.accounts.offer, which is the address of the account that we've calculated based on the seeds. And all we're going to do is just use this set inner method to go and save some stuff into the account at that address. So we provide an offer instance that we're going to make from the ID. The maker in our offer will be from accounts, tokens.accounts.maker and .key, which is their pub key. Token mint A will be context.accounts.token mint A .key. Token mint B will be context.accounts.token mint B .key. How much of token B they want in exchange, which is the token B wanted amount. And also, because this is a PDA, we will be saving the bumps that were used to calculate it, just for performance reasons. Context.bumps.offer. And then, oh, there's a typo there. That context.account should be a context.accounts. And we will also add an OK, because we're going to send this back to the top level instruction handler. That looks good. There is no red in our file. Very happy with that. So we've now finished all the functions we need for makeoffer, as well as the accounts struct that instruction handler is going to need, which specifies all the accounts that we're going to use in this instruction and how we're going to use them. So we're just going to go back into this top-level librs file and make sure that our top-level instruction handler has all the things that we want somebody to provide for this instruction. So obviously, yes, they have a context, which includes all the accounts they're going to use in this instruction, whether they're readable or changeable, or all the other things that we need, whether they need to sign the transaction. But we're also going to need them to specify an ID, which they can come up with themselves. We're going to make it so that people can't reuse IDs anyway. So it's just it's a random number that hasn't been used before. They'll also need to say the amount of token A they want. Token A offered amount, which will be a U64, and also a token B wanted amount, which will be a U64. That looks nice. And then in our make offer body, we need to specify all the things that these two helper functions are using. So instructions, make offer, send offer tokens to vault. You can see from the error that it wants a few things. It wants a context and it wants the token A offered amount. So let's give it the context, which is literally just our context from the parent, and we will borrow that. And we want token A offered amount as well. That looks good. You can see the red has gone away. Save offer also wants to use our context. We can see from the error message, it takes a context, an ID, and a token B wanted amount. So context, ID, and token B wanted amount. Save that. I've got a semicolon on the end of save offer. I don't actually need it because we're going to return whatever save offer returned. So this is just a Rustism. You can omit the semicolon from a line, and that ends up being returned by the function. That looks good. Our program should probably build at this point. We've only done make offer, which is just getting Alice's tokens into the vault and saving details about what she wants. That's good enough a time as any to go and test our program by building it. So let's do a anchor build and build our program. I'll give it a moment to finish. And we can see now that we've updated our program and it builds now, which is great. So we're now officially halfway there. Let's go create take offer. So back in our top level librs, we're going to do pub function take offer and make a new instruction handler. That is going to take a context, which is a context of take offer, which we will create in a moment, and it's going to return a result of nothing. And there's going to be two parts to take offer, which you can probably imagine. The first is taking the tokens from the vault and putting those in the taker's account. And the second is taking the tokens from the taker's token B account and sending them straight to the maker's token B account. So let's have a function for each of those. Instructions, take offer. This is going to be a file that we make. And the first function will be called send wanted tokens to maker. And we will pass it the context. And we're going to borrow the context because we don't actually need to write to it. And we're going to say if that fails, that's fine, it can fail. There might be many reasons why it fails. Maybe the person doesn't own the accounts they're trying to use. Yeah, that's fine. If it fails, then it fails. That's Anchor just doing its default checks and saying that something was wrong. And if it fails, that's fine because it's Anchor probably complaining that somebody's trying to take an offer that doesn't exist, or that one of our token accounts isn't actually owned by the taker. So that's all good. Instructions, take offer, and we will have withdraw and close vault. And it will take a context, and it will return that. Now we can see there's a little bit of red here. It's just saying that take offer, the accounts struct hasn't been made. That's okay. And the take offer file hasn't been made. So we should probably make our take offer file. So under programs, swap source instructions, new file, take _offer.rs. And let's go create take offer rs. The first thing we're going to need is, well, let's do our import of all the standard Anchor bits. We can probably get most of those from makeoffer. So I'm just going to copy all the imports from makeoffer into takeoffer, and we can remove the ones we don't use. Also in modrs, I'm also going to make takeoffer a module and expose it for everyone else. So there we go. So let's create our takeoffer account struct. So it's a pub struct called takeoffer, and it takes an account info item to set the lifetimes of various objects inside it. Also, because it's going to be an Anchor accounts struct, we need to say hash derive accounts, and I need to spell derive correctly. There we go. That looks a little bit better. And it's a capital A for accounts as well. All right. So we have a taker, which is the person who's going to sign this transaction. That's a signer whose lifetime is info. And we'll also say, because the taker is going to not only sign this transaction, but pay for the accounts to be created. So we'll say account mute, so that this we can mutate, or in other words, change the balance of this account so that they can pay for the transaction. We'll have the maker that they need to specify, pub maker, which is a system account. We'll go for the lifetime of info. And that is also mutable because they will have some of their balances changed. We'll have token mint A. And that's an interface account of info and system. Oops, not system, mint. It's a mint account. So it's interface account wrapping around mint. That just means that, again, we can use this on the older token program or the newer token extensions program. We're going to specify there's token mint A and token mint B as well. So let's specify both of those. Token mint A and token mint B. They look good. What else will we need? Well, we'll need the taker's token account A, because that's where we're going to put the tokens that we get from the vault. So pub taker token account A, and that is a box of interface account that lives for info and wraps around token account. And we'll also have the taker token account B, which is where we're going to take tokens from and send them straight to the maker's token account B. So I'll just do a quick little copy paste. I'll add that missing comma. That looks pretty good. What's it complaining about there? Just got to make sure that those are all lined up. That wraps around. Yeah, it's gone away. Excellent. Just needed to add another comma. We're going to add some anchor constraints on token account A and B. We'll say, so account, and for taker or token account A, we will say init if needed. Why init if needed? Because the taker may not have any balance of token account A. So if they've never had token A previously, when we move the tokens from the vault into the taker's token account A, we'll need to make a token account A for them. So let's do that, init if needed. And we'll also say we want to specify the mint of this should be the token mint A. So that is, also say who's going to create this this account, by the way. So payer equals taker. So I'm going to pay to make their own token A account. Init if needed. Payer is taker. Associated token mint of this account should be token mint A. And associated token authority, which is kind of the, if you think of owners in Solana are like program owners, but authority is like the account level owner. So that authority is taker. And the token program should just be the token program that we specified. So that is associated token program should be token program. Cool. So taker token account A is a box of interface account of token account. That looks good. Init if needed. Payer is taker. And the mint should be token mint A. The authority should be the taker, and the token program should be the token program specified in the instruction. A little bit of red there. What's it complaining about? A non-optional init constraint requires a non-optional system program field to exist in the account validation structure. That's okay. I haven't specified the system program yet. So once I add the system program yet, that error will go away. So we've got the taker token account B. And let's add some constraints here. Account. And this will be mutable because its balance will change. And all we need to do is copy some of our constraints from earlier, but this is taker token account B, so we need to make sure that we're checking that it is the token mint B, not token mint A. That looks good. There's another account that another token account we'll be mentioning here, which is when we will take tokens from the taker's token account B, and we'll send them to the maker's token account B. So pub maker token account B, and let's add some constraints. So Anchor can check all these good things for us. The maker's token account B will also be init if needed, because the maker, again, may not have ever had any of these tokens before. So init if needed. Payer to create this account will be the taker. And the mint, authority, and token program, I'm going to copy and just double check. So the mint for the maker token account B should be token mint B. That's good. The authority is not the taker, it will be the maker, because this is the maker's token account. This is Alice, this is not Bob. We need to make sure that Alice owns Alice's account that holds token B. And the token program is the token program they specified in the instruction. That is all good. Finally, oh yes, we're going to involve the offer account. So the offer is just an account who will live for the lifetime of info, and it's of the type offer. And what do we need to add to this? Well, let's start our little anchor account constraints. This will be mutable. Why? Because we're going to close this offer account when the offer is taken. We'll also, when we close this account, we will also return the soul in it back to the maker. Why? Because the maker made the offer account in the first place. So it seems fair that when we close this account, we should refund that back to the maker. Close equals maker. And we're going to just do some little, we're going to specify some things we want to exist inside the struct. So has1 equals maker, has1 equals token mint A, has1 equals token mint B, and the seeds for this are exactly the same as what they were before, which is the bytes of the word offer and the maker's key as _ref. And the offer ID, offer.id.2 little endian bytes. So we have it as bytes as ref. There we go, that looks good. And finally, the bump equals offer.bump. Always save your bumps. That looks good. Excellent. What else do we need? We need the vault, because obviously this take offer is going to move tokens from the vault. And yes, you can probably already imagine that the vault will be mutable. So let's go set that up. The vault is an interface account, lives for the lifetime of info, and it is wrapping around just a regular old token account. Again, if we weren't doing this, compatibility between the older token program and token extensions program, Vault would just be token account, but because we want this compatibility layer, the best practice is to use these interface accounts everywhere. So we have our account, and the Vault is obviously going to be mutable because we're going to take all the tokens out and we're going to give them to the taker. And the rest is just making sure that the mint of the token account is exactly what we expect. So I'm going to copy these, but I'm also going to check them. So the mint of the vault will be token mint A, because we took tokens from the maker's token account A and we put them in the vault, and they will be of the mint A. The authority of the vault account will neither be the maker or the taker. The vault account is actually, its authority is the offer account. This means that the vault is controlled by the offer. It's not controlled by the maker or the taker. It's controlled by the offer, which is the offer account can actually sign for things. And when we send tokens from the vault, they will be signed for by the offer's own account. And our token program will be our token program. That looks good. Save that. And finally, we've got the normal checks about all our programs. I'm just going to copy those from make offer. System program, token program, and associated token program. Thank you very much. I will paste those in. And that looks good. No errors, no warnings. Just a couple of unused imports. That's okay. I'll delete them once I've finished writing this file. So we've made our take offer struct, which is going to specify all the accounts that we need to check as part of an incoming take offer instruction. And we've created the top-level instruction handler in librs, which we called takeOffer. And back in librs, we said we wanted to have two functions. One was called send wanted tokens to maker, and the other was withdraw and close vaults. So in takeoffer.rs, let's create the first of those two functions. So to make that send wanted tokens to maker function, we'll do pub function send wanted tokens to maker. And that's going to take a context, which is a context of make offer. And we're going to borrow that item as well. Also, that's going to return a result of nothing. And let's make that happen. So this is actually just going to be very simple. To send the wanted tokens to the maker, I send the tokens from taker's token B account straight to the maker's token B account. It's just going to be transfer tokens, our little helper function we made earlier. And the from will be, we'll borrow this, context dot accounts taker token account B. The to will go to the maker's token account B. Context dot accounts dot maker token account B. The amount of token B to send will come from the offer. So that's context dot accounts dot offer dot token B wanted amount. The mint will be and context dot accounts token mint B. The authority, i.e. the person who controls that account, will be the taker. And the token program will be context.accounts.token program, token underscore program. That looks good. And this is a context of take offer. I did notice that my autocomplete was a little bit funny there, so that explains it. I think I said I wrote make offer when I should have written take offer. So there you go. So yeah, that actually looks good. So we're transferring tokens from the taker's token account B straight to the maker's token account B. We're transferring the exact amount that the maker wanted. We're making sure the mint of the accounts are token mint B. We're checking that the authority of the from account is the taker, because this transfer is going straight from the taker to the maker. And we're just making sure the token program is the same one that we specified in the instructions. That looks good. So we've just completed our send wanted tokens to maker function. The final part for take offer is to complete the other helper function we made, which is called withdraw and close vault. So let's make that now. Pub function withdraw and close vault. And it's going to return a result of nothing. The options it will take are just simply the context again. Context. And that's the context of take offer. Now, we're going to do a transfer here, but it's not going to be a transfer from a regular account. Instead, we're actually going to transfer from our Vault account, which is owned by our offer account. So this is a PDA transfer. It's a transfer that's being signed for by our offer account itself. So we're not going to reuse our helper function, which is focused on a different type of transfer. We're going to make our own calls to transfer checked with a slightly different set of options this time. So we make the seeds. Which we will borrow. And the first of the seeds will be the bytes for the text offer. You might remember this. This is the seeds we used to get the address of the offer account. So we're going to use that to actually sign this transaction. The second option, the second seed for that account will be context.accounts.maker to account info .key.as.ref. What else will we need? The offer ID, context.accounts.offer.id.2 little Indian bytes. I'll do a little bit of magic on it there. And then finally, bump, which we'll borrow, context.accounts.offer.bump. We'll also want to borrow that offer ID. So let's, that looks good. Little semicolon. We can actually have multiple signers when we do a transfer from a PDA like this, but we only have one in this case. So we're going to wrap our seeds into a bigger signer seeds array. Let signer underscore seeds equals bigger array and just our seeds. Do a little magic there. That looks good. We're going to make the accounts that are going to be involved in our transfer checked function. So that is let accounts equals transfer checked. This is really the options for our transfer checked. From context.accounts.vault.to account info, comma, mint. Actually, let's do the 2 first. I think it's a little bit more. Context.accounts.to is the taker. These will go to the taker's token account A because we're going to take the accounts from the vault and put them into the taker's token account A because the tokens in the vault are of the type token A. Taker's token account A, oh yes, to account info, comma, the mint, which is context.accounts.taker token mint A, remain obviously to account info, and our authority, which will be our offer account. Context.accounts.offer.to account info. Final comment there, and doesn't like transfer checked. It's okay, we just need to import it. Import transfer checked from token 22 or token interface. I'm pretty sure I want the one from token interface. That'll allow us to use both older and new token programs, but let me double check. Yeah, that looks a little bit better. There's actually a transfer checked right below token interface, so make sure you import that one, and not the really long one that I imported. that is happier now. Excellent. So we've got our accounts all set up for this token transfer we're about to do. We're going to make a little CPI context. Let CPI context equals CPI context new with signer. And all we're really doing here is combining the accounts, which are effectively the options for transfer checked, the token program, and the signer seeds, which allow us to sign for this transaction as the offer. So the program will be context.accounts.token program to account info. I might actually, like the next time I get some time free, I might make a little wrapper for this because I'm getting tired of typing to account info. Maybe you are too. And accounts and signer seeds. That looks good. Oh, we just want to borrow that and it will be happy. Yep, that looks good. No red. The only red there is our result. That's fine. We haven't actually written the code for the result yet. What's next? We've got our CPI context, and let's actually do the transfer now. So that's transfer checked. And takes a context, which is our CPI context. It takes the amount that we're going to transfer. So that's we're going to get that from the vault. So context dot accounts dot accounts dot vault dot amount. There we go. And the decimals. Context dot accounts mint token A dot decimals. Token mint A decimals. That's complaining. It wants me probably to import it. Cannot find function in that scope. That's fine. Import transfer checked. And we probably want to import it straight from token interface. So not token 22 and not token. I think there's I think we can just import it straight from token interface manually. Let's do that. Comma transfer checked. And there. That looks good. There's a little bit of red elsewhere. What's this? Check that out in a moment. Oh, I think. Oh yeah, that's just it saying that we need to do our return, which is fine. We've done our transfer checked, which is taken that's the withdrawal part of withdraw and close vault. That has moved the token A tokens from the vault into the taker's token A account. Great. If you're wondering why we need to provide the decimals for transfer checked, it's part of the checked part of transfer checked. It includes some safety checks like making sure that you explicitly provide the decimals. So we've moved our tokens from the vault into the taker's token A account. The other part of this is to close down the vault itself so it can't be reused. So we're going to make a close account struct, which is going to be the options that we provide to another CPI to the close account function. So let's do that now. Let accounts, and it will equals close account. We have three options: the account, which will be the vault itself, context.accounts.vault, and to account info. We'll have our destination, which is where we're going to refund any LAMP ports that were in that account. We'll send them to the taker, but we could send them to the maker as well. Context.accounts.taker.to account info. And the authority, which is who's allowed to, who's doing this, which is the offer. The offer account owns the vault. That's context.accounts.offer. And you guessed it, to account info. That looks good. I needed to import close account, by the way, as well. I've done that right at the top here, and it comes directly from token interface. So make sure that you import things from token interface, not from the old token program specifically, not from token 22 specifically. Import from token interface. Great, so here's our accounts. Let's make a CPI context so that we can go and invoke our close account function. That's a CPI context and new with signer. The program will be context.accounts.token program and to account info. The accounts we've actually already specified above, and signer seeds. I think we just need to borrow that and it should be okay. Yep, that looks fine. And then, so we have our CPI context, everything we need to go and invoke close account. Let's actually invoke a close account. Close account. And yeah, CPI context. Oops. What's it saying there? Mismatch types. Ooh, I can see what I'm doing there. I am not using the right version of close account. So let's just go back to my imports and double check that. Yeah, I've got token close account. I want token interface close account. It's one thing to be really careful of when you're using an editor that suggests imports. Do make sure you're importing everything from token interface, not from the token program. And you'll see that that's now fixed. Great, and I actually can omit the semicolon because we're going to return whatever closed account returns from this function. That looks good. So we've created our make offer, we've created our take offer, the high-level instruction handlers and all the helper functions and the structs of accounts they need. Let's go and review librs. We've got our take offer, withdraw, and close vault. That all looks good. We should probably check that our program compiles. So back over here in our terminal, let's do a anchor build. A couple of unused imports, that's okay. I might actually get rid of those just for the sake of cleanliness. We weren't using anchor discriminator. Ooh, we need to handle any errors in transfer checked. So what we can do with that is we can say a little question mark there, and that says, look, if transfer checked throws an error, throw an error. That's, that's okay. We can deal with that. That looks a little bit better. So back in our compiler, let's clear the screen, anchor build again. And that builds. We now have a working swap program where someone can offer their tokens to be taken, and then someone can take that offer and receive those tokens directly in their own accounts. So we've run our program and it builds. Next step is to test it. We've already got some tests we've prepared for you, but I'll go through them here. This is swap.ts under the test directory, and it's pretty simple. We import a few common bits and pieces, anchor itself, the chai assertion library, the Solana helpers, make a few variables, and we have one block of tests called swap. That connects to Anchor, which allows Anchor to use the keys and the networks set up in our anchor.toml. And we set up some variables we're going to use in a moment for Alice, Bob, token mint A, and token mint B. Our before handler is really simple. It just creates some users, some mints, and some token accounts, and uses those mints to mint a particular balance of tokens, so that Alice has a lot of token A and that Bob has a lot of token B. There's two tests, and the first is our make token test. Make sure that it puts the tokens Alice offers into the vault when Alice makes an offer. So we're simply going to get our list of accounts together, and then send that transaction off. Program methods.makeOffer with our options, the accounts we want, and our signer is Alice. Afterwards, we're going to check the balance of the vault, and we're going to check the offer account has the data that we expect. The second test is pretty simple. It's program methods.takeOffer, confirms the transaction, and checks Bob's accounts after running the test. Also, we could add a test to make sure that the vault is closed. I don't think we are here, but I can add one in a moment. You'll also note I run .slow, and then I have a variable set to, I think it's 60 seconds. Because Anchor tests connect to our local validator, by default, Anchor shows them as slow because Mocha actually shows them as slow because they take anything that takes more than, I think, half of 30 seconds is shown as slow. So if I set my slow threshold to 60 seconds, anything that takes half of 60 seconds will be shown as slow. Our tests only take 15 seconds, so they won't be shown as slow. You didn't really have to worry about that too much. It's just a me thing. I hate my tests being shown as slow. I like to establish a bit of a baseline for how long a test should take. So yeah, pretty simple. We just have one describe block and a test that goes and checks make offer and another test that checks take offer. If we run those, and you can import them into your own program, you can get them from the link that we will add to this presentation. You can actually call your take offer and make offer and check that they work as expected. Give it a sec. As I said, these tests take about, I don't know, maybe 15, 16 seconds each. And then we can see the first test is finished, which is puts the tokens Alice offers into the vault when Alice makes an offer. And in a moment, our second test should hopefully finish as well. There we go. Puts the tokens from the vault into Bob's accounts and gives Alice Bob's tokens when Bob takes the offer. So this program is a great example of the benefits of DeFi. Alice had some of one token and wanted another token. She didn't know Bob. Bob, at some point in the future, came along, took that offer that Alice made, exchanged his tokens for Alice's tokens, and each side got 100% of what the other person was offering without anyone in between taking a portion of anything. Also, the other useful thing about this program is that it shows you how to handle tokens in your own program, to how to hold tokens, and how to sign to transfer those tokens out of places where they're stored using CPIs. So I'll see you in the next lesson.